Okay, gang, I hope chapter 1 didn't blow your mind too much. So let's go ahead and get cracking on chapter 2. Your objectives for chapter 2. Explain the role of awareness level personnel during a hazardous material incident. Describe basic precautions for providing emergency care to victims of a hazardous material incident. Identify common ignition sources found at a hazardous material incident. Describe some ways in which hazardous materials are harmful to people and the environment. Describe the routes of exposures to hazardous material for humans. And describe the routes of exposure to hazardous material for humans. Operation level objectives. Describe the types of stress that can cause a container to release its content, the ways in which containers can breach, and some of the dispersion patterns created by the release. Identify timeframes for estimating the duration that hazardous material presents and risk of exposures. Describe the following properties: boiling point, chemical reactivity, corrosivity, and flammability. Flash point, ignition temperature, particle size, and persistence. Describe the following properties of the physical states of a solid, liquid, and gas: radiation, ionizing and non-ionizing, specific gravity, and the toxic products of combustion. Describe the following properties of vapor density, vapor pressure, water soluble, and physical changes as well as chemical changes. Describe radiation as well as the difference between alpha, beta, and gamma rays and neutrons. Describe the differences between the following pairs of terms: contamination and secondary contamination, exposure and contamination, exposure and hazard, infectious and contagious, acute and chronic effects, as well as acute and chronic exposures. Describe the following types of weapons of mass destruction: blood agents, biological agents and toxins, choking agents, and irritants. Describe the following types of weapons of mass destruction: nerve agents, radiological material, and vesculants, also known as blistering agents. Describe the health and physical hazards of exposures to hazardous material. Describe the health hazards associated with the following: alpha, beta, gamma, and neutron radiation, asphyxiant, carcinogens, and convulsants. Describe the health hazards associated with corrosive, highly toxic, irritant, sinister allergen, I know I murdered that word and I apologize, and target organ effects, as well as toxic. So, in this chapter, we're going to start off by looking at the chemical and physical properties. And that's an important first step in understanding the hazards associated with any chemical involved with the state of matter. Examples of chemical and physical properties are vapor density, flammability, corrosivity, and water reactive. And we'll go more in depth on what each one of these are. But for now, know that vapor density is how heavy a gas is in relation to air. So when they do terms of vapor density, it's either heavier than air, meaning that it will sink and go to low-lying areas, or either it's lighter than air, meaning that it will kind of float away and disperse. Flammability is how flammable something is. Corrosivity is how corrosive a substance is. And water reactivity is how it will react to water. Now, it is not necessary to be a chemist to respond safely to hazardous material incidents. I'm not going to lie, if you have a chemistry background, it does help. But in most cases, you can be guided by careful observation, referring to your emergency response plan or standard operating procedures, and correctly interpreting the visual clues that are presented in front of you. So with our first step, let's look at the properties, and of course it can either be a solid, liquid, or gas. Knowing the state of matter helps predict what the substance will do if it escapes from its containment vessel, which will influence the incident's duration as well as your emergency response plan. Ways containers can be breached include disintegration, runaway, cracking, closure, opening up, punctures, splits, and tears. And here are good examples of each. The state of matter and other physical properties help determine how the substance will escape. For example, is a release gas heavier or lighter than air? And as I said earlier, if it's heavier than air, and that refers to the vapor density, it's going to sink and congregate in low-lying areas, or either it's going to float away. The dispersion patterns could be cloud, stream, plume, pool, hemispheric release, cone, and irregular dispersions. Here's a good example of a liquid dispersing as a stream and a gas dispersing as a plume. Pooling, as seen here, and your hemispheric release, which is categorized traditionally as an explosion, as such as a liquid propane tank exploding. Here's a picture of a cone release, and again that goes to the pattern, and your irregular dispersion, where basically your water is kind of going every which way. Now, your physical and chemical changes can help determine or estimate the duration of the event. And remember, chemicals undergo physical change when they're subjected to certain things, such as heat, cold, and pressure. For example, when frozen, water changes from a liquid to a solid state. Despite this change, the chemical makeup is still H2O. Water can also be heated up and changed from a liquid to a gas. And for example, liquid propane, like the kind used to power your grill, is in a liquid state because it's under pressure. Once it begins coming out of the tank, it is no longer under pressure, thus turning it into a gas. An important term to remember is a BLEVE, and that is a boiling liquid expanding vapor explosion. This condition is caused by a pressurized liquefied material inside a closed vessel exposed to high heat. The substance in the vessel exposed to high heat will begin to expand and change from a liquid to a gas, eventually causing the container to breach and rupture. And if it's flammable and the conditions are correct, it can explode. A good example of this is your propane and butane. The expansion ratio is a description of the volume increase that occurs when a liquid changes to a gas. Propane has an expansion ratio of 270 times to 1. So, for every 1 volume of liquid of propane, 270 times that amount of propane exists as a vapor. Chemical reactivity, also known as chemical change, describes the ability of a substance to undergo transformation at the molecular level, usually with the release of some form of energy. Physical change is essentially a change in state. By contrast, a chemical change results in an alteration of the chemical's nature of the material. So examples are steel when it rusts and wood when it burns. Physical and chemical changes as they relate to you. You are the responder case study. Assume for the moment the owner of a landscaping company watered up some rags soaked with linseed oil and left them in the corner of the shed. The rags ignite spontaneously. And this is going to be a chemical change because linseed oil generates heat as it decomposes and comes in contact with oxygen and ignites. Fire caused the failure of a propane cylinder, and that's a good example of a BLEVE. Another chemical change is fire melted a fusible plug on a chrome cylinder, causing the release of chlorine gas. Basically, the gas mixes with the moisture in the air and forms an acidic mist, which comes in contact with firefighters' skin and eyes to cause irritation. Chlorine gas is 2.5 times heavier than air, so plenty of eye irritation were located on the bottom floor of the complex. Critical characteristics including flash point, ignition temperature, and flammable range. Only substance in a gaseous or vapor state will combust, essentially burn. Solids and liquids will produce vapors, then ignite. So basically anything will burn when it turns into a gaseous state and the conditions are correct. The minimum temperature at which a liquid or a solid gives off sufficient vapors such that when ignited the vapors will result in a flash fire is known as flash point. Some ignition sources examples are an open flame, electrical equipment, lightning, and static electricity. For example, the flash point of gasoline is negative 45 degrees, meaning gasoline that is basically negative 45 degrees and up will give off a flammable vapor. And then, when it's exposed to some sort of ignition source, it will burn or explode. Flashpoint only involves the vapor phase of a liquid, which comes out once the vapor fuel is consumed. Common substances with a low flash point are gasoline, ethanol alcohol, and acetone. Now, number 2 grade diesel fuel has a flash point resulting in lower ignition temperature and lower vapor pressure. When the temperature increases, so does the production of vapor by flammable liquids. So for example, with diesel fuel, its vapor point where it'll ignite is totally different from gasoline. So at 125 degrees Fahrenheit, 52 degrees Celsius, diesel fuel reaches its flash point. So until that point, diesel fuel will not burn. So to put this in perspective, if you have a gallon of gasoline in an open container, you strike a match, you drop it in the container, you'll get a nice explosion, and of course the vapor will ignite coming off the gasoline, and it will continue to burn until all the vapor and liquid are gone. If we did that same demonstration with diesel fuel, you strike a match, you drop it in the diesel, it'll do nothing but put the match out. Reason being, the diesel fuel, it's not at its vapor flash point yet. So you have to heat diesel fuel up first in order to get it to burn. So this brings us to fire point, which is a little different. And at fire point is when the temperature at which a sustained combustion of vapor will occur. Essentially, it's one of those, okay, now the liquid is burning, so it will continue burning until you're out of fuel. And that's your fire point. It is usually only slightly higher than the flash point for most materials. With that being said, you actually have to have your ignition temperature right. And maybe, like in the case of gasoline, a simple match will do it. However, with diesel, it will not. Another type of temperature ignition is auto ignition. And that is basically when something will spontaneously or auto ignite, which is the minimum temperature, as I said, which a fuel, when heated, will ignite in the air and continues to burn. There is no external ignition source, and in the case study, they used the example of linseed oil. So here's another example. A pan full of cooking oil on the stove, left unattended on a burner, set on high. It will ignite once the oil is heated past its ignition temperature. This is a common cause of stove fires. Flammable range. Expression of fuel and air mixture defined by the upper and lower limits that reflect the amount of flammable vapor mixed with a given volume of air. These basically are the boundaries necessary to burn, and you have your lower explosive limit and your upper explosive limit. If it's below the lower explosive limit, it's said to be too lean, and if it's above the upper explosive limit, it's said to be too rich. So anything outside of that range, and then the product will not burn. So for example, you have a gentleman working in a pit that has a pipe going through it. The pipe has an opening and is releasing natural gas. That individual working in the pit decides to light up and smoke a cigar while he's working on the pipe. Will it explode? And the answer is probably not, because at that particular area, it's going to be over the upper explosive limit, so the fuel is too rich. There's too much fuel, not enough oxygen, so the mixture is not correct. Now, if that individual gets out of the hole and begins walking away, it's quite possible that they could wander into that area that's between the upper and lower explosive limit, and then that would obviously create fire and an explosion. Here's an example of gasoline. The lower explosive limit is 1.4% and the upper is 7.6%. The wider the flammable range, the more dangerous that material is. Here's some other common flammable ranges of common gases: hydrogen, natural gas, and propane. See how hydrogen has a very wide range, so that makes it a very dangerous gas in terms of combustion. Vapor pressure applies to the liquid held inside any type of closed container. All liquids, including water, develop a certain amount of pressure in the airspace between the top of the liquid and the container. The vapor released from the surface of any liquid must be contained if they are to exert pressure. And the great example of this is your Coke or Pepsi products. You know how you got the can there, and when you crack the lid, that pressure is released. Another good example, you take that same Coke can or Pepsi can, you leave it in the sun on a hot summer day out in your car, what's going to happen? Well, the vapor pressure is going to grow higher in that can till it either A, ruptures the can or kind of blows out and mushrooms the bottom of the container. That's a good example of your expanding vapor pressure in relation to heat. Liquids with high vapor pressure evaporate much more quickly than liquids with low vapor pressure. A good example of that would be alcohol-based things like regular gasoline or some sort of ethanol alcohol. If that's poured on the ground, it evaporates rather quickly. Now, if you take diesel and pour it on the ground, you know it's going to sit there for a while. Vapor pressure is expressed in pounds per square inch, which is psi, as well as atmosphere, torr, millimeters of mercury, and bar. So when you're looking at these measurements, 14.7 psi equals 1 atm, which equals 760 torr, or 706 millimeters of mercury, which also equals 1 bar. Boiling point. It is the temperature at which a liquid will continually give off vapor in sustained amounts. If held at that temperature long enough, it will turn completely into a gas. At water, boiling point of 212 degrees, the water molecules have enough kinetic energy to overcome the downward force of the atmospheric pressure. So basically, the heat is considered energy, and that energy is transferred to the water in the form of heat, which causes the water temperature to get raised, again causing the energy to be released throughout the molecules, and that energy reaches a certain point which causes the water to boil, which makes it turn into a gas. Vapor density is the weight of an airborne concentration of a vapor or gas compared to the equal volume of dry air. So air has a set vapor density of 1, and everything is compared against that, as I said earlier. So anything greater than 1 in vapor density means that it's heavier than air and it'll sink. And if it's less than 1, it's lighter than air, and it will cause the gas to sink. So your vapor density essentially affects where the gas is going to go when it's released. In the field, in the absence of a reliable reference source, you can use this mnemonic to remember lighter than air gases, and that is 4H metic Anna. And that basically stands for hydrogen, helium, hydrogen cyanide, hydrogen fluoride, methane, ethylene, diborane, helium gas, carbon monoxide, ammonia, neon, nitron, and acetylene. Again, that acronym is 4H metic Anna. And those are all gases with a light vapor density. Now on the flip side, when we're talking about water, it's kind of similar, and that is referred to specific gravity. So this compares the weight of a liquid chemical to the weight of water. Again, if the water has a specific gravity of 1, anything heavier than 1 will sink and go underneath the water, and anything lighter will float on top. So when you're looking at oil, as seen here, notice that it is floating on top of the water, so it has a specific gravity less than 1. Most flammable liquids will float on top of water. Examples are gasoline, diesel fuel, motor oil, and benzene. Water solubility is the ability of a substance to dissolve in water. Water is the predominant agent used to extinguish fire. But when dealing with chemical emergencies, it may not always be the best or safest choice to use. It can react violently with certain chemicals such as concentrated sulfuric acid, metallic sodium, and magnesium. Fog streams may be used to knock down vapor clouds depending on the chemical that is involved. Corrosivity is the ability of a material to cause damage to skin, eyes, and other parts of the body upon contact. The technical definition is destruction or irreversible damage to living tissue at the site of contact. Now, it'll also damage clothing, rescue equipment, and any other physical object in that environment. Corrosive are a complex group of chemicals that should not be taken lightly. There are basically tens of thousands of corrosive chemicals out there, and a lot of them are acid-based. So if we look here at this pH chart, and pH can run from 0 to 14 as listed on the right hand side. And here are your examples. Hydrochloric acid has a pH of 0, meaning it's very acidic, and sodium hydroxide has one that is 14, which is very, very base, or alkalotic. When we're looking at acids, we said acids are, and bases I should say, are measured in pH. And you have specialized testing papers that are used to determine the actual pH level. Now, 7 is considered neutral. Anything above that is more of a base or an alkalotic substance. Anything below that is more of an acid. Now, what is pH? pH is simply a measurement of hydrogen. So the more hydrogen something has, the more acidic it becomes. And I've always thought that is confusing because you would think if it had more hydrogen, the number would be higher. But in the case of the scale, it's actually lower. So the increase of hydrogen makes stuff more acidic. The decrease in hydrogen starts making it more of a base. A good example would say be bleach. Bleach is actually a very alkalotic substance, and if you took bleach and you put it on your finger, you would notice how it's very kind of slick and slimy. Where if you took more of an acidic substance and you put it on your finger, I don't recommend it, it's going to start being more corrosive and eating away at it. So pH values of 2.5 or less and 12.5 or more are considered extremely strong. So you can have a strong acid or a strong base. Strong corrosive reacts more aggressively with metals, skin, or other chemicals and water. Awareness and operation level corrosives are complicated and tactics needed may be outside the scope of their responsibility. Toxic products of combustion. Hazardous chemical compounds can be released when a material decomposes under heat. Combustion is a chemical reaction, and like other reactions, generates byproducts. So essentially, fire is a chemical reaction, and it generates waste. Smoke products by a structure fire is something that we're a lot familiar with. But what is in the smoke? And that essentially is toxic gases. And those toxic gases can be cyanide, hydrogen sulfide, and all carbon monoxide, carbon dioxide, you name it. So a lot of asphyxiants and cancer-causing materials. Fire smoke includes soot, carbon monoxide, carbon dioxide, water vapor, as I said, and of course cyanide compounds and oxides of nitrogen. And they can be toxic even in small doses and can cause difficulty with oxygen transport, and which leads to asphyxiation. So basically what cyanide does, it prevents, and even carbon dioxide and carbon monoxide to a point, it prevents the red blood cells from transporting oxygen to the rest of the body, which essentially causes you to suffocate. So let's look at radiation. Radiation is energy transmitted through space in the form of electromagnetic waves or energetic particles. Radiation can come from many sources such as the sun, soil, and X-rays, as well as occupational exposures encountered in the field through some sort of radioactive type product. Health hazards posed are determined by the amount of radiation absorbed by the body, the exposure time of the radiation. And you can look at the periodic table for the list of the radioactive elements. Elements are made of atoms, which are comprised of protons, neutrons, and electrons. Variations in the number of neutrons create radioactive isotopes. Radioactivity is the process by which unstable atoms, which are isotopes, of an element decay to a different state and emit or radiate excess energy. Typically, you will encounter a combination of alpha, beta, and gamma radiations. Responders can wear small radiation detectors on their turnout gear. As seen here in this chart, you have your alpha rays, which can easily be blocked by fabric, beta rays, something simple as a door, and gamma rays will actually go through the fabric and the door. So really with your gamma rays, the only true defense is basically lots of water, lead, as well as copious amounts of concrete. Alpha particles have weight and mass, but cannot travel far at all. So it's really less than a few centimeters. So if you stay several feet away from a source that has alpha radiation, wear a filter, long sleeves, some general clothes, or simple respirator or SCBA turnout gear, and you'll be fine. Beta particles have more energy than alpha particles and pose a greater health hazard, and they can travel up to 10 to 15 feet in open air. And this is considered ionizing radiation. What is ionizing radiation? Basically, ionized radiation is radiation that can cause changes in your human cells, which could possibly lead to cancer. Good examples are, of course, X-rays and gamma rays. Non-ionizing radiation comes in the form of electromagnetic waves, and there is no sufficient energy to change the human cells. Examples of non-ionizing radiation can be sound waves, radio waves, and microwaves. Beta particles may cause reddening and burning to the skin, damage to the tissue only when inhaled. Solid objects traditionally provide adequate protection. However, you should wear some form of positive pressure respiratory protection like an SCBA. Now, gamma radiation is pure electromagnetic energy. The most energetic radiation that responders may encounter. It has no mass, no electrical charge, and travels at the speed of light. It passes easily through thick and solid objects. It is considered ionizing radiation and can be extremely deadly. The neutrons can create gamma radiation, and SCBAs will not provide protection for you, or I should say adequate protection for you. Neutrons. Neutrons are the penetrating particles found in the nucleus of the atom. Exposure can create radiation. Responders must observe the scene and establish a safe perimeter. A hazard is a material capable of posing, again, unreasonable risk to health, safety, or the environment that is capable of causing harm. Exposure to the process by which people, animals, the environment, and equipment are subject to or come into contact with a hazardous material. Contamination is the residue of a released chemical, and decontamination is the process of removing that substance or chemical release from the person. Now, a couple of terms that I really want to make sure we get right in our brain. Exposure is when you are actually exposed to a chemical by means of absorption through the skin or inhalation. Contamination is kind of like when you come in contact with something. So, let's use the example of, say, dog poop. If you step in dog poop, are you contaminated or are you exposed? So, since you can take the shoe off, the shoe is still contaminated, but you no longer are, so you're not really exposed to it. However, if you take that same dog shit, and excuse my French, and you eat it, now you are exposed to it because now you have ingested it and it's been taken into the body. Secondary contamination, also known as cross-contamination, occurs when a person or object transfers the contaminant or the source of the contamination to another person or object by direct contact. So again, we have that dog poop and it's on her shoe, and now you walk inside. Now the floor inside is a victim of secondary contamination, as the shoe kind of is the primary contamination. Responders often have the misconception that PPE is worn to enable them to come in contact with the product at will. In fact, PPE is worn to protect you in the event that you cannot avoid product contact. Essentially, if you don't have to be in it, don't be in it, guys and gals. Because if it's wet and not yours, you probably don't want to play in it because you may get something that soap and water won't cure and penicillin won't take away. My PPE speech in a nutshell: wear it and don't play in it unless you absolutely have to. Okay, gang, another acronym for you, and I apologize, there is just a ton of acronyms, but they're supposed to be meant to help you remember important information. So when we're looking at weapons of mass destruction, which have really come to fruition in the current years in the media, and should definitely be something responders look into because it is definitely a real threat. There are 7 types of damaging weapons of mass destruction, and TRACEM P is the acronym that they use, and T stands for thermal, R radioactive, A asphyxiation, C chemical, E Etological, such as anthrax, plague, and smallpox. M is mechanical, and P is psychogenic. So let's look at nerve agents first. They enter the body through the lungs or the skin, and they essentially disrupt the central nervous system. When it does that, it can cause serious impairments such as blindness, loss of muscle control, vomiting, lacrimation, urination, defecation, and even death. A good example of a nerve agent is sarin gas. Now, when you're exposed to nerve agents, here's another, I know, acronym to remember. SLUDGEM. So if you see somebody that is salivating, meaning they're just like drooling at the mouth like they have rabies, lacrimation, urination, defecation, or gastric disturbance, such as diarrhea, things of that nature, nausea, vomiting, then the odds are they have definitely come in contact with some sort of nerve agent and need to be treated effectively, as well as you need to be protected. Emesis and mylosis are another two, which is vomiting and constricted pupils. A good example would be VX gas, which is the most toxic of weapons in terms of nerve agents. Now, the next one is a blistering agent. And when we're looking at blistering agents, they are also known as vesculants, and they have the ability to basically cause blistering of the skin. Common agents can be sulfur mustard and lewisite, which were often gases that were used during World War I. So your mustard gas was first used in World War I. It is in a liquid state. It is colorless and odorless if pure. If it's mixed with some stuff, it may have a brownish tinge with a strong odor of garlic or onion smell when it's mixed. And if you're exposed to mustard gas, the signs and symptoms usually occur anywhere between 2 to 24 hours after exposure. Here's a good example of what would happen to your skin when exposed to mustard gas. The injuries are very similar to second and third degree burns, and inhalation exposure can lead to respiratory function impairment and even death. Lewisite has many of the same characteristics of the mustard gas. It is also considered more like an arsenic type thing. The exposure symptoms may mimic the arsenic poisoning, and skin exposure causes immediate pain. It is considered a chemical warfare agent. Its high concentration leads to convulsions, inability to breathe, loss of consciousness, and death. So convulsions are a fancy medical term for seizures. Another one to be wary of, blood agents. And these are chemicals that interfere with the transfer of oxygen from the blood to the cells. So inhaled, ingested, or absorbed through the skin can cause this problem. Examples are cyanide compounds. Typical signs and symptoms of exposures are vomiting, dizziness, watery eyes, deep and rapid breathing. High concentrations can lead to your seizures and an inability to breathe, as well as loss of consciousness and, of course, death. Choking agents. They inhibit breathing. They are having a very extreme irritant odor, kind of like, your pepper gas. They are intended to incapacitate, but may in fact kill or cause serious injury, and in the way of causing pulmonary edema, and that's known as dry drowning. Essentially, your lungs fill up with fluid, and the oxygen, carbon dioxide can't get out of your body, so you suffocate or essentially drown. Examples of choking agents are phosgene, chlorine, and chloropycerin. And this acts as a skin irritant, causing significant burning in higher concentrations. Irritants. They cause pain and burning sensation when exposed to skin, eyes, and the mucous membranes. So a good example of this would be mace. It is used to temporarily incapacitate a person or a group of people. A form of terrorism perspective may be employed to incapacitate rescuers or to drive a group of people into another area where a more dangerous substance can be released. This is considered one of the least toxic of the WMD group. Decontamination, which is basically getting the stuff off of them, can be formed with simple clean water. Effects are meant to wear off. Convulsants can cause convulsions or seizures when absorbed by the body. Examples are sarin, soma, taboon, VX, and organic phosphates, and carbamate pesticides. Essentially, they interfere with the central nervous system and disrupt normal transmission of the neuromuscular impulses, basically the signals that control your muscle movement. So when you think to pick up your hand, you're not going to be able to do it because that signal that comes from your brain to your hand is disrupted by this chemical. Some pesticides function as a convulsant and can be fatal in very small exposures. So how does this stuff get in the body? So now we're going to look at routes of entry. And it can be inhalation, meaning that you breathe them in, so it gets in your body through the lungs. Absorption, by touching the skin and permeating, meaning going through the skin. Ingestion, meaning that you eat it. And injection, it gets in the bloodstream or the body by means of cuts or other breaches in the skin. Here's your good example of inhalation, ingestion, injection, and absorption. Now with inhalation, exposures occur when harmful substances are brought into the body through the respiratory system. It can be such things as corrosive material, solvent vapors, and superheated air, as well as infectious and contagious organisms. A self-contained breathing apparatus is most important piece of PPE for firefighters. This can have a full face and a half-faced air purifying respirator known as APRs, as seen here to the right. And this is just a way to get fresh air and keep the nasty stuff off. Now, SCBAs and APRs. OSHA says any work environment containing less than 19.5% oxygen, because 21% is about normal, that's what we walk in every day, requires the use of an SCBA or supplied air respirator. They can be more comfortable and allow for longer work periods with the supplied air respirator, that is. So if you're in something that has less than 19.5% oxygen, you need to be wearing some form of respiratory type protection. Now, the anticipated particle size that you're going to come in contact with can dictate the level of respiratory protection. So here are some measurements in terms of hazards you may come in contact with. Fume, smoke, dust, fog, and mist. So whatever your respiratory protection you pick should be able to filter that size contaminant or particle out. If someone encounters anthrax, it requires an SCBA or full face APR with a P100 filtration, meaning it filters everything. Infectious organisms capable of causing an illness is known as, of course, infectious, and contagious is capable of being passed along to another person. So here's a couple of key terms that we need to remember. Now, when you look at your respiratory system, depending on the size of the contaminant, this gives you an idea of where they will end up at. So if it's less than 7 microns, you're looking at the nose, so it'll get filtered out by the cilia and essentially the mucous membranes in the nose. 5.7 microns ends up in the larynx, 3.5 microns the trachea, 2.3 microns it ends up a little further down to the bronchi, and 1.2 the respiratory bronchi, and then of course the smallest part of the respiratory tract is the alveoli, and that is something really small at 0.521 microns. Now we said absorption is the process by which a substance travels through the body tissue until they reach the bloodstream. This can occur through the skin, eyes, nose, mouth, and the intestinal tract. The body may produce an asphyxiant as a byproduct. Asphyxiants prevent the body from using oxygen. Essentially what they're saying here, it could cause like an allergic reaction. And that's when your body produces a reaction to this foreign body that causes your throat to swell and your blood pressure drop, and leading to basically cardiac arrest through suffocation. An example of that would be like a histamine release. Some of the agents are cancerous in causing, meaning carcinogens. Aggressive solvents are readily absorbed through the skin, such as alcohol, paint thinner, things of that nature. You should evaluate the possibility of chemical contact and determine if your protective gear is sufficient. So if it's something that's like a solvent that's really wet, more than likely like fire coats and whatnot, they'll offer very limited protection. You need something that is more durable or plastic-like. Ingestion, the chemicals are brought into the body through the GI tract. This may occur when rotating out from an emergency response and not taking time to clean up. So prior to eating or drinking, make sure you take a shower, wash your hands, and get all the cooties off you there. Injection, the chemical enters the body through that open cut or abrasion. Oftentimes when I think of ejection, I think of like a needle going underneath the skin in the body. But here in this text, it is basically considered any opening in the skin where stuff can get in. So address cuts and open wounds before you report to duty. Make sure they're covered with band-aids, duct tape, tegaderm stitches, whatever the case may be. If significant, you may be excused or excluded from contaminated environments. Open wounds act as a direct portal to your bloodstream. So, chronic health hazards. After long-term or chronic exposure to a hazardous substance, you can develop chronic health conditions. Now, they can also appear after multiple short-term exposures. And you're going to have target organs that are going to be affected, such as lung trouble or COPD emphysema. And a good example of that would be the asbestos exposure, or for coal miners, black lung. Now, acute health effects occur after relatively short-term or acute exposures, and they produce observable conditions such as eye irritation, cough, dizziness, and skin burns. Examples can be acid burns from sulfuric acid, breathing difficulties, and skin irritations from exposures to formaldehyde. Rounding out the list, we have toxicity, which is a measure of degree to which something is toxic or poisonous. So that's kind of looking at the adverse effects. So LD is considered lethal dose. LC is lethal concentration, and OSHA descriptions are based on lethal dose as well as lethal concentration. LD is the lowest dose per unit of body weight of a substance known to have resulted in fatality. So median, which would be LD 50, which means 50% of the people exposed to this level die. That's what it's basically saying here. OSHA defines toxic as chemical with an LD 50 between 50 and 500 milligrams per kilogram via oral administration. Chemicals with a LD 50 between 200 and 1,000 milligrams per kilo via continuous contact with spare skin for 24 hours, and chemicals with an LC in air between 200 and 2,000 parts per million via continuous inhalation for an hour. OSHA defines highly toxic as chemicals with an LD 50 of 50 milligrams per kilogram or less via oral administration, chemicals with an LD 50 of 200 milligrams per kilogram or less via continuous contact with bare skin for 24 hours, or chemicals with an LC of 50 in air or 200 parts per million or less via continuous inhalation for 1 hour. So, now that your brain's really hurt, you got a lot to go over, of course, a lot to read and review questions. So let's review some of the key points. The most fundamental of all actions is your ability to observe the scene and understand the problem you are facing. Think before you act. It could save your life. An important first step in understanding the hazard of any chemical is identifying the state of matter and defining whether the substance is a solid, liquid, or gas. A critical step in comprehending the nature of the release is identifying the reason why the contaminant vessel failed. Chemical change is not the same thing as physical change. Physical change is a change in the state. A chemical change describes the ability of a substance to undergo a transformation at the molecular level, usually releases some form of energy. So physical change is like from a solid to a liquid to a gas. A chemical change is like mixing, water with an acid. And then the product that comes out is, maybe something a little more acidic. So that's changing the water's chemical makeup. Now, there are many critical characteristics of flammable liquids, and you should be familiar with each of them. And those are the flash points and upper and explosive limits and things of that nature. When responders respond to hazardous material incidents, they must fully understand the hazards to minimize the potential for exposure. Avoid contamination whenever possible. It will reduce the likelihood of harmful exposures. The chemicals can enter the body in 4 ways: inhalation, absorption, ingestion, and injection. Nerve agents, blistering agents, and blood agents, choking agents, irritants, and convulsants are all examples of hazardous materials that fall in the WMD category. Irritants such as mace cause immediate irritation of the skin, eyes, and mucous membranes. Equipment such as APRs and SPAs can protect the lungs from selected particulates such as smoke, dust, and fumes. Finally, chronic health effects may occur after years of exposure to hazardous material. Make sure you wear all protective gear to minimize the impact of repeated exposure. Okay, gang, so make sure you go ahead and read the chapter if you haven't already. Do the review questions. And if you have any questions, feel free to email me at aroberts@athenstech.edu or call me in the office at 706-357-0162. Until next time, be safe and have a wonderful day.